So in this part of the lecture, I will give you an overview of the finite potential well. The quantitative analysis of this problem is quite involved, so I will just give you an overview, and perhaps we can go into some of the detail in an assignment or a quiz or something like that. Okay, before we go into the quantitative discussion, let's discuss a few things qualitatively. So recall that when the potential had a height v0, so it was not infinite, that in region 1, 2, and 3, this is 1 and 2 and 3. In region 1 and 3, the wave function had the form of a e to the power minus k1x plus b to the power plus k1x. So if you take it to be region 3, then we saw that as x went to infinity, x went to positive infinity, this part of the wave function blew up. And that was not physical for like an energy which is less than the total potential energy, if this is our energy, because that would imply that a particle in the the kinetic energy or in this region is negative. So this is a disallowed region, as this is, and if this was not zero, that would mean that the probability of the particle being found farther and farther away from the allowed region would be increasing, so that would not be physical. So for this to be physical, we have to set b is equal to 0. So as a result, what we'll have is that we'll have left this thing, and this is an exponentially decaying part, so it decays like this over here, and that's a completely physically acceptable solution in the case where the potential well, it has a finite depth. So similarly, over here there'll be a potential a wave function which will be decaying like that, and in the meantime, in the middle, we'll have a wave function which looks like the free wave function that the sine and cosine wave function that we derived earlier. However, these three wave functions need to satisfy the continuity condition at this point and this point. And because the potential here is finite, there will be two sets of continuity condition. One would be the continuity of the wave function itself across this boundary. Another one would be the continuity of the first derivative of the wave function across this boundary. And it's these continuity condition which leads to the quantization of energy. Another observation that we can have is that if I look at the wave function which is in the middle, and it's going to be the solution to the, it'll be a sine or cosine kind of wave function, but it doesn't have to go to 0 at the boundary because the potential well is finite. And therefore, although this is sine and cosine, if we were to continue the cosine beyond these walls, then what we would get is, they would go and, end up somewhere over here. So if we consider, this, the wave function in the middle region as being part of a wave function of a system which had an infinite potential well, then we would see that infinite potential well width would have a larger width than the finite potential well. And remember that the energy of the infinite potential well, the particle in a box, went like 1 over L squared. And because the width of the infinite potential well would be bigger than the potential well which we are actually solving, therefore we see that the energy associated with this wave function would be lower than the energy that we would associate with an infinite potential well. So let us now move on to a more quantitative discussion of the finite potential well. So let me redraw the finite potential well, and I'm going to use slightly different parameters now. So this is my potential V of x, and this is my x-axis, and here I'm going to choose the potential to have a negative value of minus V naught. So V naught is a positive number, but the potential at x equals to 0 to x equals to a is negative. All right, so we can write this potential analytically over here as it's 0 when x is when x is less than a. It is minus V naught when x is greater than 0 and less than a, and it is 0 when x is greater than a. All right. So again, we know what the solutions are. At least we know their forms. We have done this before. So our wave function will have 3 regions, and region 1 will have e to the power k1 of x, where k1 is given by minus 2me divided by h bar. So we're taking e to be a negative number, so e is something like this. So we are looking for bound states. We are not looking for positive, like energy states like this. This is not what we're looking for. So e is a negative number, so k1 is a positive number. And then in the middle region, we have the solutions, which are the oscillating solutions. And in region 3, we have the decaying solution again, which is of this form. Now note that I chose the coefficient of the first wave function to be 1. And the reason for that is that because, at the end of the day, I am going to be normalizing this. Therefore, it's only the relative normalization of all these different wave functions which matter. So I can always choose this to be one of them to be 1. Okay, so we have then actually 3 constants, A, B, C, that we can play with. But now we have to impose the continuity condition at this point and this point. And the continuity condition, oh, by the way, let me also tell you what it is. K is going to be 2m e plus V naught square root divided by h bar. So the boundary conditions, if you impose this, then we get 4 sets of equation because we have 2 boundaries, and there is the boundary condition that we have to impose on psi on both boundaries as well as psi prime. So there's 4 set of conditions, but we have only 3 independent, 3 parameters to play with. So what this means that, the boundary conditions cannot be satisfied for all values of the energy E. That the boundary conditions will put some constraints on the possible values of E. And that is basically what leads to the quantization of energy. So the conditions that we get from the boundary conditions are A plus B is 1, and K1 is equal to IK A minus B. So I'm leaving this as an exercise. Then C to the power E to the power minus K1A is equal to A e to the power I ka plus b to the power be to the power minus I ka. And then lastly, it's going to be, so these are all derivatives, this one and this one. C e to the power minus k1x is equal to I of k a e to the power I ka minus b e to the power minus I ka. Anyway, so you can solve these, and if you solve for the energies for the k's, you get a relationship which is cot of ka is equal to k by k1 minus k1 by k. And this is the condition that one needs to solve to find out the value of the energy. It turns out that this is a condition that cannot be solved exactly. So if we introduce, say, gamma to be 2m v0 a squared by square root divided by h bar, and alpha to be ka by gamma, and this is equal to 1 plus e by v naught square root, then this equation can be converted into a transcendental equation. And this equation is going to be gamma alpha n minus 1 pi plus 2 cosine minus alpha, where n is an integer 1, 2, 3, dot, dot. So to solve this, one needs to plot the left-hand side and the right-hand side, and look at where the intersections are. So if we do this, then so the graph looks something like this. So we are going to, so this is our y-axis. I'm going to plot both functions in the y-axis, and this is the x-axis. In the x-axis, we are going to plot alpha, and alpha goes from 0 to 1, and this is going to be pi, this is going to be 2 pi, and this is going to be 4 pi, and this is going to be 6 pi, so on and so forth. And what we're going to do is that the right-hand side, if you plot the right-hand side for different values of n, 1, 2, 3, for n equals to 1, this is 0, so we just have this guy. So in that case, we are going to have something which looks like it goes down and then it goes like that. And then for the next one, it'll just be shifted by 2 pi. It's the same thing, but shifted. And here it's shifted, and here it's shifted. And right. So the first one is going to be 2 cosine inverse of alpha. The second one is pi plus, say, 2 cosine inverse alpha. And the next one will be, this should be 3 pi, and this should be 4 pi. And so the next one would be 2 pi plus 2 cosine inverse alpha, and the next one would be 3 pi plus 2 cosine inverse alpha. All right, and the left-hand side is just a straight line, so it'll have, it'll go like this. Actually, the lowest one will only intersect this one, and then this could go like that, and that could go like this. So this is, for example, gamma is equal to 1, and this is going to be gamma equals to 4, and this is going to be gamma 12, so on and so forth. Anyway, so energy eigenstates, the energy solutions are given by the number of intersections. So let me use different colors for the different values of gamma. So this is a different configuration, and then this is another configuration. So like that. Okay, so so this is a bit subtle, but the idea is the number of intersection points and hence the energy states are given by the number of integers which are below this number, gamma by pi plus 1. And to see this, you have to look at this equation and set alpha equals to 1. So you're looking at this extreme end of this graph. And what you're saying is that you're going to look at, okay, how many of these curves does my line intersect? And you can show that it's the number of integers which are contained within this number is the number of times that this line is going to intersect this guy. Okay, this guy. So that's how you find the number of energy eigenstates you have for a given value of gamma. So one thing to note is that what is gamma? If I look at gamma, gamma has in it the depth of the potential, V naught. So if I make the potential deeper and deeper, then gamma increases. So that means that the slope of this line becomes bigger and bigger. And so we get more and more energy levels. So as the well gets deeper and deeper, we get more and more energy levels. And the other thing to note is that if I look at the wave function, if I look at the this wave function, the one in the middle, and I solve for A, B, and C, then I get an interesting expression for psi. And it turns out to be, I'm not going to derive this, in the middle, so is going to be 1 over alpha sine of k x minus a by 2 plus n pi by 2. This is for x greater than 0 and less than a. And one thing to note is that for a given n, this function has n minus 1 zeros. Okay? So that means that in total psi, so this is in the region 2, right, in the middle region. So that means that in total psi has n plus 1 zeros. And why is that? That's because in the middle of my potential, this guy has some sinusoidal behavior, but then these guys go off to 0 at infinity, right? So there are these zeros at infinity. So those you have to count as well. So it turns out that for the nth energy, it turns out that this is a general phenomena, that for the nth energy level of a one-dimensional bounded system, the wave function has n plus 1 zeros. So of course this is a very nice and qualitative result, which is independent of the details of the potential, and it's actually a theorem.